Alright, so we stopped yesterday doing these. I showed you potassium, neon, and O2 negative. I didn't do sodium, but the plus sign means that it has a positive charge of +1. We usually don't write the 1 when it's just 1. So if it was a -1 charge, we'd write just a negative. But if you work out for sodium plus, you also get the same thing as O2 negative and neon. All three of those have the same electron configuration as just pure neon. We'll explore why they get the same charge whenever they become ions as neon later in the year. But let's look at excited states. So the electron configuration, we usually mean the ground state in which all the electrons are in the lowest possible energy level. Some electrons can be knocked up to higher energy levels. Excited atoms are unstable energetically. The electrons will eventually fall back down to a lower level. Now, if we come and look back, we haven't covered electromagnetic waves yet. Way far back. But whenever an electron goes up into a higher orbital, it takes energy to do so. And when it falls down, it has to give off energy too. And when it falls back down, the energy it gives off is usually visible, or usually some form of light. For example, this is of a hydrogen atom. Usually, the electron is only in S1 or 1s because a hydrogen atom only has one electron. But if you were to bump up the electron into higher energy levels, when it falls back down to a lower energy level, it'll give off a type of light. There are the wavelength of light, the color of the light depends on which energy level it bumps up to and which energy level it goes to afterwards. We can see that it gives off ultraviolet, infrared, and a few visible. In particular, you can see the red color when it goes from N3 or energy level 3 to 2. This is what happens when you burn hydrogen, and it gives off a very red light. Has anyone ever burned hydrogen? Let's see, there's a picture. That's for burning. So if you've ever burned copper, you'll see green. That's because electrons are being bumped up. You're heating it up, giving the electrons energy, and when they fall back down, they produce light. And different colors, we'll learn this later on in the next unit. So for example, lithium's ground state is 1s2, 2s1, but electron can bump up, and we donate a cited electron configuration using asterisk. So 1s2, 3p1 is not the ground state because 2s1 is lower than 3p1. There's a nice shortcut too. So instead of using Aufbau's rule, we can look at the periodic table and actually figure out the electron configuration of the periodic table. So if you've ever wondered why the periodic table is shaped the way it is, do you see a pattern? The first two columns are all S subshells. The transition metals in the middle are your d orbitals. The right hand side is the p orbitals. And helium is an exception. Helium we usually put with the noble gases because it's the noble gases. So we put it on the right hand side. You could argue that it should go on the left-hand side next to hydrogen, because it is 1s, but it's the exception. And then the ones at the very bottom of the table all have f orbitals. So the left-hand side are going to be your s orbitals. Note that there are only 2 possible electrons that can go into s orbital, hence 2 columns. There are 10 d orbitals, which is why the transition metals are 10. There are 6 electrons that are, or I should say, there are 5. There's 3 orbitals, but 2 electrons can go in each one. It's giving you a total of 6 electrons for the p. I was saying that wrong. There's 5d, which 10 electrons can go into them all. So if we wanted to randomly pick something from the table, so let's pick one. Let's do aluminum. So aluminum has 13 electrons. And if we use Aufbau's rule, we're going to start with 1s, then 2s, then 2p, then 3s. We'll stop there and go ahead and 2, 2, 6, that's 10, which means I have 3 left. 2 is going to go in here, which makes 1 left, which means 3p is the next one. And I'll put that 1 on the p. So using this diagram, we can write the electron configuration. However, if you have a periodic table and you memorize this information, let's read the periodic table. So it is right here. So on this diagram, it'd be right here. So we see, if we read it left to right, 1s, and there's 2 of them. Then we have 2s2, and then we have 2p, there's 6 of them, so 2p6. And we keep going to the next one, 3s2. And it's in this column right here, so 3p, and it's only the 1 bulk of the 3p's. So let's look at a more complicated one. One that is more bigger. Let's do arsenic. So arsenic has 33. So instead of trying to count the 33 electrons and keep filling it up according to Aufbau's rule, we can read left to right. So this would be one. Arsenic is right here. So we'll start at. So 1s2, then 2s2. There are 6 of these, so 2p6, then 3s2, then 3p6, then 4s2, and there's 10 Ds, 3d10, and then 1, 2, 3, 4p3, and we're done. Does this seem a whole lot simpler than using this method? This one allows you to quickly look at it. You can use either one you want. This is just giving you an option. I will say, however, when we start abbreviating using the noble gas abbreviation, this method is far superior. Also, you can immediately tell what the last one's going to be. The last one is going to be 4p3. And you can double check. So that's 10, 20, 32. Wait. 30 and then 30. 10, 20, 30, and 33 for arsenic. Personally, I like this method better for the larger ones. Because once you get to the larger ones, writing the whole thing out is very time consuming. There's a way to abbreviate it that I'll discuss here in a second, which is the noble gas core electron configuration. So let's look at sodium. Sodium's configuration is 1s2, 2s2, 2p6, and 3s1. As you can see, this kind of gets very long very quickly. There's a way to abbreviate this. And what we're going to do is just replace the previous noble gas configuration to substitute for the initial terms. So if we look at the periodic table, sodium, by the way, the noble gases is anything in the last column. Helium, neon, argon, krypton, xenon, and radon are all noble gases. If we look at sodium, sodium is number 11. If we look at the previous noble gas before it, which would be neon, number 10, we can just replace the configuration for we're using neon. So the preceding noble gas with atomic number less than sodium is neon. We can rewrite the configuration as neon with brackets 3s1. This is where this technique makes it way more easier. So let's look at arsenic. So arsenic was right here. And so looking at this element, the one preceding it, so we were to go back, this would be the noble gas right here preceding it, which is argon. So this is argon, and this is arsenic. So I can abbreviate arsenic's noble, write it as noble gas electron configuration as argon, and then just write the column 4s, 2, 3d10, and 4p3. This is the abbreviated noble gas configuration. It removes this from here down, making it a lot easier to write. So neon completes the So neon completes the 2p subshell. Sodium marks the beginning of the new row. So we can write the condensed electron configuration for sodium as neon 3s1. Neon represents the electron configuration of neon. The core electrons are make up the noble gas, and everything outside of the core is called the valence electrons. I would say that everything outside of it on the last energy level. Looking back at I would say that the highest energy level, these are the valence electrons. I would not consider the 10 electrons here as being part of the valence. A little mistake on the PowerPoint. So I've been calling this the longhand is technically called the orbital filling diagram. This is where you actually fill out every single one with up arrows and down arrows for the electrons. So remember Hund's rule and Pauli exclusion. Pauli exclusion say you can't have two ups in the same orbital. You can't have two downs on the same orbital. You can only have at most a single up and a single down. Hund's rule states that we will fill all the p's trying to maximize the same spin. So looking at nitrogen, there's 3 ups before we started filling 2px. So there are some exceptions to electron configurations. Some actual electron configurations differ from those assigned using off-ball principle because half-filled sublevels are not as stable as filled sublevels, but they are more stable than other configurations. Exceptions to the off-ball principle are due to subtle electron-electron interactions in orbitals with very similar energies. Copper has an electron configuration that is an exception to off-ball's principle. It is actually the number one exception that we look at. It's also, this exception is why copper is so good at conducting electricity. Because the electron doesn't want to fill the lower orbital, it puts it up into a higher energy level, which makes it more easier to come off, allowing it to conduct electricity better. So let's look up copper's actual electron configuration. Or let's work it out first using off-ball rule. So, copper has 29 electrons. It's located right here. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is its correct, or this is its configuration according to off-ball's rule. And I personally like using the periodic table because of how quick I'm able to generate this. But let's look at, let me actually write the orbital diagram for this. So we have our 1s, our 2s, our 2p, 3s, 3p, or 4s. So filling it out, we'll do each subshell first. Then we do ups. Then we do downs. Starting with the lowest energy first. And there should be only 9 in this one. So according to Aufbau's rule, this is how we should fill it. But this is not the actual electron configuration of copper. This is an energy level 3, and this is an energy level 4. Technically, this has higher energy than energy level 4, but look at how many electrons are in this one, and look at how close it is to being full. What ends up happening is this electron actually gets bumped up and goes into this one. So it actually becomes 3d10 and 4s1 is the actual electron configuration for copper. As I said, you don't have to do these exceptions. You don't really have to memorize them. Copper is an exception. And usually anytime you see the D's at 9, so for example, silver is going to be 9, gold is going to be 9. These usually follow exceptions. Let's look up. So copper electron configuration. So we see 3d10, 4s1, so that's an exception. Let's look up gold. Is gold an exception? Gold is also an exception. The D is filled before the S. Silver is an exception, I believe. Yes. So if you can fill the D, so if D is is at 9, what happens is it's more likely to try to fill this because it's so close to being full. But you guys can ignore this exception and just write it according to Aufbau's rule. I wanted to go over one more example. So let's look at gold. So looking at gold. Gold is right here. So looking back at here, gold is right here. So doing the noble gas for it, this will be the previous noble gas, which corresponds to xenon. So going back, xenon is the previous noble gas for gold. So writing for gold, which is AU, the noble configuration for it, xenon, and then we read the row. The row would be 6s2, but after 6s2, what comes next? 4f. Note that these right here are squeezed into this spot right here. So when reading the row, after 6s2 technically is 4f14. Then we have 5d9. Again, technically gold is an exception. This electron actually bumps up to this one in real life, but you can ignore exceptions. So y'all think y'all got electron configuration down? No. The same thing as the top. Technically, this is the first page, because it doesn't matter what order you do it in. This was technically the first. So, definitions for, well, I guess, never mind, this was the first page. But for 4, 5, 6, 7, 8, 9, these have a mistake in it. Circle the mistake, and then explain, then put which rule it breaks. So each of these has a mistake in it. They either violate Aufbau's rule, Hund's rule, or Pauli exclusion principle. So circle the mistake, and then write next to it what rule it breaks. What little blanks? These blanks? So to give you an example, number 4. What rule does it break? What's wrong with it? How are you supposed to... Yes, number 4. So looking at 2p, remember you're supposed to put a maximize spin. This is correct, which this is wrong. The arrows are just electrons. This is wrong. If you're putting 2 electrons into 2p, according to Hund's rule, you should maximize same spin before you add a down. What do you mean? The arrow is a single electron. An electron can have a spin up or a spin down. Every box is an orbital. An orbital can have at most 2 electrons. This is a spin up electron, and this is a spin down electron. So at most, an orbital can have 2 electrons. It can have an up and it can have a down electron. Do you get it now? So in this example, Hund's rule says that when you're putting electrons in, you're going to start by putting all the ups in first. So when we put in 2 electrons, you cannot put an up and down in yet because you have to put in ups first. So if you're putting in 2p2, 2p2 would look like this, not like this. Does that make sense? So when you have in real life, you have these orbitals. You can put in an electron into them. So here's one electron. And I'm going to have it spin up. And this whole thing right here is one orbital. And Hund's rule states that when you add another electron, it has to go to another orbital. And it has to be spin up too. So when I put it another one, so I'm adding another electron into it, that has to go into another one. And it has to be spin up. So representing each one as boxes, that's adding it to 2 different orbitals. Adding in a third one would then have to go into another one, and it has to also be spin up. And we cannot add another electron. We cannot add another spin up because Pauli exclusion tells you that at most each of these orbitals can have at most only one spin up. So in order to add another electron, the electron has to be spin down. And when you add it into this one, it'll be a spin down electron, and it'll feel this. If I add another one, it would have to be spin down. And then add the next one, it would also be spin down. So each of these boxes represents so we start, I'm using boxes, but you could just use lines. So all of this is 2p. So how many electrons? So at most, 2p can hold at most 6 electrons. How many electrons do you want to use? Pick a number between 0 and 6. 4. Alright. So let's add 4 electrons. So I'm going to put 4 electrons in this. At most, it can only be 6. What you're going to do is add an electron. By default, we start with up. The next electron we add, so we added it to this spot right here. Each line can only have 2 electrons at most, and it has to be an up or a down. If we add in the second, so you said we're going to add 4. The second electron also has to be up. But Pauli exclusion says we cannot have 2 ups on the same line, the same orbital. So we have to put it on the next one. And the third electron is going to also have to be up too. And we can't have 2 ups on the same line, so we're going to add it to the third. The fourth one cannot be an up because we've already used every line has an up in it. The fourth electron has to be a down. And so I'm going to add that. This would be sp4, or sp with 4 electrons in it. Each line is an electron. Does that make sense?